Warm welcome to everyone. Good morning to you, and then greetings of the day when you're connecting from outside Singapore. I know few of them are connecting from India and other countries. Warm welcome. And again, Anil has explained, I've already taken a session with Singapore Telugu Samajam on data
Warm
science.
welcome.
Sorry, I hear something.
No, you go ahead.
Okay, great. So where was I? Yeah. So I've taken a session on data science and career opportunities last month. And then, as I said during the fireside chat with Piyush, it's going to be a 2-series session. So on the first session, I already talked about data science, but by then it is also important to cover the niche technologies, especially something like quantum computing. Okay. So today we're going to see that, right? So what is quantum computing, and then what are some of the career opportunities in this topic? I want to set some expectations before we proceed. What I would request you to notice or give attention to, this topic is very niche. It's a very new topic. Very few people in the world, right, are actually know quote unquote what this quantum computing is. So having said that, the concept is very niche and new. Some of the underlying concepts are also very technical in nature compared to the data science session that I provided last month. So this gets into lots and lots of technical jargons, definitions, and also it might expect you to have a basic knowledge of physics and computers. But don't worry. I think two important points here, right? Take down the notes, take down the concepts. If you really don't get it during the session, what I want you to do is you do your own research over the computer or over the internet, and then get familiarized with the topic. Because I myself, right, I could not able to get everything in my first quantum computing conference. So I need to take notes, go research myself, get deeper into the concept, and that's how I got familiarized with this concept in like last 3 years or so. I think you need to do the same, and especially young students who are connected in this call, right? This is a very good opportunity if you're opting for careers in the computer science and also wanted to do a niche, you get into a niche industry or a niche technology, right? I think this is the technology that I think you should look into. A lot of skills shortage, especially next 5 to 10 years, it's going to explode across the world, right? So, and then for students especially, you need to familiarize with this topic and be prepared yourself. And last but not the least, this is also available as a YouTube link later, right? So if you guys don't get anything in this session, you can always play back. You can always pause and then understand the concepts a little deeper. Don't worry, if you don't get the concept, ping me or do your own research. I think you'll be fine. Okay. So with that note, let's get into the agenda or how your knowledge path will look today, right? Just like last time, it's divided into 3 sessions. First, I'll take some time and then walk you through what the quantum computing is with some examples, use cases, and then trends and current state, right? What's happening in the quantum world, where is the current state, and then how it's going to go from here is what I'm going to focus here. Third, last but not the least, what are some of the opportunities and then support, especially from a Singapore ecosystem and government in this quantum computing? Unlike data science, here I'm not just going to focus only on Singapore, right? Because this is a very niche technology. So Singapore is also also like not so advanced in this particular topic, but just there. So which is why I need to quote examples beyond Singapore, which is why I think I'll also share you some global links, international links that are helpful in developing the quantum computing career. But as such, Singapore government is very clear, crystal clear on promoting this across the Singaporeans, and then working to bridge the skill gap in next 5 to 10 years. Okay, so with that note, let's get started. Okay, first topic on quantum computing overview, right? Before we even get there, I have a small quiz for you, right? Can you tell what this is? Can you guess what this is? Treat this like an icebreaker, maybe, right? But if you remember, some of you are very, I mean, at least have a good understanding of the computers. I think they can relate what this is. Maybe I think if you know the answer, obviously, I think you cannot reply in the group, but at least you can answer yourself. But you know what this is? This is the first digital computer. This is the first electronic digital computer built during World War II by United States, right? It is called ENIAC, the Electronic Numerical Integrator and Computer. And then what it'll do the multiplication, subtractions, and additions. And then it's a room full of the transistors that you could see here is how the first computer should look like. I mean, at least look like. Correct? It's a very, very huge room just to do a small calculation. That's how the computers were in 1950, right, or 1940s. And also to surprise you, right? Can you tell me what this is? This is also one of the first computers, but there is a good prominence of what this particular computer is. If for the people who thinks like companies like Japan, India, Singapore, started using the computers only in 1990 or 2000, you're wrong. So this particular computer is India's one of the first analog computer, right? Designed by ISI, Calcutta. And then it was discussed and displayed to Nehru, and it's one of the first computers used by India. It's an analog computer. And similarly, I think the other computer that you saw is a 1960 Ural computer, right? So the famous Mahalanobis. I think recently Google also built a doodle commemorating their contribution to the Indian computing, the Indian and Asian computing system. So some of these computers by Mahalanobis are collaborated with Japan, Fujitsu, and India, and then being operated across multiple countries. And some of these are also operated by Singapore at a later part of the time. So with this note, right, what I want you to tell you is the computers that you handheld in your hand, right? Even I would say a phone that you have in your hand, right? This itself is like a very powerful technology. See how we emerge, right? A room full of transistors and then circuits, integrated systems, and then we come to something that you could able to hold in a pocket, or probably that you could able to put onto your wrist and then operate, right? So that's the journey or evolvement of the computers in past, I would say 70 plus years, correct? So fundamentally what happened, so it goes by the Moore's law, right? So people, again, who are non-technical, you can go and research what Moore's law is. But what he said is the computing power, right? The transistors or the circuits that it takes to build a powerful computer. He predicted that it's going to go two times every particular period of time, right? So which is what exactly happened. So the transistors, which were as big as a room, now what's happening is it's becoming like a nanometer size. So, but what is the problem with that? For example, can we build something very, 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 very small nanometers? Even can you break the nanometers and then go beyond and still build a very powerful physical computer or a classical computer? May not be. So which is what I'm going to focus in the next slide, right? What are some of the limitations with the current computers that we have? This is interesting. Huh? Just give your thoughts here for a moment. The computer chips are getting smaller and smaller, right? It's already approaching the 14 nanometers, and there I heard there is also like 8 nanometer chips, 4 nanometer chips coming. This 14 nanometer chip itself, right, is 8 times. It's basically 8 times the HIV virus diameter, and this is less than 500 times smaller than the red blood cell. But that's not the problem, right? Here in physics, until the atomic level, so which is 2 nanometers, right? It's okay. So because it follows the day-to-day physical laws that you see. But imagine if you want to build a computer chip beyond 2 nanometers, for example, this 14 nanometers, you want to break through 2 nanometers, you know what happens? That's where the problem is. The physics, right? The laws of physics does not apply beyond nanometers because it'll get into a subatomic level. So this is where exactly the subatomic level, it behaves in quantum principles. Again, you could go and do the research yourself. When I say quantum principles, right, the gates that we use, the diodes and gates that we use at a subatomic level, there are, what basically happens is they put up barriers and say, if it could not able to cross the barrier and it is 0, and then if it could able to cross the barrier and it is 1, and that's how you maintain that zeros, ones, bits maintained in that chips, right? But what happens is, beyond 2 nanometers, you cannot simply put a barrier between the subatomic particles. Why? Because it follows a quantum principle, and then basically it can freely move between any barriers that you can keep. It's called quantum tunneling. I don't want to get into some of these concepts, but I'm trying to understand, right? Anything beyond the 2 nanometers chips, it's very hard to build because it behaves in quantum principles. And how many of you know, right, blockchain? Very famous solution, right? As you know, the fundamental or even simpler question, right? How many of you know RSA tokens that you use to log in during your office laptops or connect to the VPNs, etc.? So basically, what's going on here? They're all encrypted devices, and then they use something called factorial based encryption. So meaning it's a concept. I think you can do the research itself, right? The problem here is you have the Shor's algorithm, which proved that if you have a very, very powerful computers, you can break this encryption. You can break this encryption. So coming 5 to 10 years, let's say if you have very powerful supercomputers and all that, you might as well, the factor-based encryptions does not work, it will break. And then this factor-based encryption is also fundamental concepts between the blockchains, right? So the blockchains are immutable. The contracts happening between the blockchains, the records that you put into the blockchain, if you put today saying that, I paid Anil $100, and then if you put it into the blockchain, the reason why it is a trusted entity is because you cannot rewrite this record. So meaning once you put it there, you can only add on top of this, but you cannot edit or remove this record from the block. Why? Because all these chains are protected by the encryption. But imagine tomorrow, if I have a powerful computer, what happens? I can immediately break this encryption, and I can write some other contract even before my $100. I can say that Anil gave me $200 and I paid him $100. Net on it, he owed me $100. That's possible. So, and then it's theoretically proven. And then some of the AI models and all that, right? The training data, etc. They're all encrypted based on the same factor-based encryption, and then it can be broken, correct? So that's why the current factor-based encryption doesn't make sense. And then this is interesting, right? How many of you know what's happened in the COVID? The reason why any pandemic that hits us, and then to find a vaccine, to find a medicine for some of these pandemics is taking time. It takes about 2 years, 3 years, and beyond that, right? Luckily, in this COVID arena, the scientists have worked really hard, and then even the trials are like accelerated, and they got it approved as an emergency basis from the US, and then rolled out the drugs. But let's say tomorrow a very critical pandemic hit, wherein the 2 years is not sufficient, right? Probably you might need to act within days to find a medicine. So how do you then do it? The current physical computers that you have, right, it is not suitable to model the nature. So if you want to understand the biological protein structures, chemical molecules, which are chemical molecules, and even gene mapping, right? The current classical computers will take years to even do it. Even the supercomputer will do will take about 2 years, 1.5 years to simulate a particular drug, the drug simulation, right? So it's very, very computing intensive. So which is why you need a natural way to model and simulate and derive insights if you want to model the nature. The current physical computers does not work. That's why I think the concept of a quantum computer works. Don't worry if you don't get any of these concepts right. Probably you can take the notes and then do the research yourself. You'll be able to understand what I'm talking here. Okay. So with that note, we know that there are limitations with a physical computer, and then you need a quantum computer, right? But what is that? What is this quantum computer? Let me get into the next slide and then help you explain what that is. What is quantum computing and how is it different to a classical computing? Classically, if I ask you what are the prime factors of 17, people who know mathematics, right? It's very easy. They say only 1 and 17. There's nothing else that comes in picture, right? So for example, if I ask prime factors of 91, you could say, the prime factors of 91 are 191, 7 and 13. Maybe you take a little bit of time, but I think you would be able to tell. Humans can tell, right? Up to certain digits, up to 2 digits, 3 digits. I've seen humans easily telling what the prime factors are, correct? Take this example. 232-digit numbers, prime factors, right? Which is exactly what happens in the encryption, or probably which is exactly what happens in the background of drug discovery. You know how much time does it take for a computer to crack this? If you put your i9 Intel core processor, right, and then ask you to calculate the prime factor for 232 digits, you know how much it will take? It will take 2 years to find the answer. It'll take 2 years. Why? Because as you could see here, right, the time and computing power required to calculate grows exponentially as the integer increases, correct? So meaning, because we run on bits, zeros and ones, right? So how the computer works, it'll arrange these zeros and ones in a combination and then calculate and then throw the answers in zeros and ones, and then it decrypt and put you onto the screen, correct? That's a time computing, that's a time taking process. But I'll tell you, if I put the same calculation in quantum computer, right? It's a sophisticated approach which works on the subatomic particles and quantum mechanics. And then it can calculate 232-digit prime factors theoretically within like 1 to 1.5 hours. So on one side, a physical computer will take about 2 years to get a sizable amount of money to get the answer. On the other hand, there is a technology that will give you answer in few hours. How is it possible? Let's understand a little bit more what's happening behind this. Yeah, so this also comes to my next point, right? How does the quantum computer work? Classical computers, as I said, do you know, right? For example, if I ask you what is 100010, for people who are learning the computers newly or from your engineering days, it's A in binary language, because our computers, the one that I'm using and giving this presentation, right, it only understands ones and zeros. Our classical computers are built on bits. It's also called bits, right? Ones or zeros. So at any point of a time, if I have a diode which is like 0 and 1, it can store 2 memory units, right? So which is basically either 0 or 1. And then let's say if I keep on adding these diodes and put that integrated circuits, let's say if I have 10 diodes, so basically it can store 20 memory units, correct? Maximum, that's about it. And then on the other hand, quantum computers are built on a concept called qubits. Note this down, people who wanted to understand the quantum computers more, right? You keep hearing this term again and again. It's called qubit. Our physical computers are built on bits, and then this is built on qubits. And then qubits is not 1 or 0. It can be both at one time. So it can store more memory per unit. I can explain to you with a very simple example. For example, consider this as the US coin, right? So consider this as heads and tails. Basically, I can say if I get a head, maybe this is 1. If I get a tail, maybe this is 0, correct? So if I toss a coin and then if it comes ahead, and then you can say, hey, that's 1. And then if I get a tail, no, that's 0, correct? That's exactly how the bits works. Let me ask you this simple question. Is this 1 or 0? Let's say it's spinning. The coin is spinning, right? If you clearly see this, it's both 1 and 0. It's between 1 and 0, right? Based on the time at which you observe and then see the spin. So it could be slightly 0 and slightly 1. This is exactly how the quantum computer qubits work. The qubits are basically is nothing but you use something, a quantum concept called superposition. Okay, so what is superposition? You spin the atom, right? You don't put it in a single state. You put the atom into a spinning position, and then when the atom is in subatomic particles are in spinning position, right? So basically, it's not 0 or 1. It could be anything. And don't worry, for the first time, you'll not get what this is. Again, I'm telling you, you go to the you go to the computer and research what the qubit is. Probably you'll be able to understand a bit more. And then what's happening here is because this particular qubit can store multiple values, not just zeros and ones. See, from a layman perspective, right? I can tell you what this is. It works in a concept called entanglement. So basically, what happens if I have one qubit and if I have another qubit, I can entangle them together, meaning I can pair them together. So if I change the state, even this particular second qubit is also changes. With that, right, I can tap enormous computer power. And it has been proved, by the way, using some small qubits, which are actually available in the market, right, via IBM, Google, and all that, which I'll explain what that is. Theoretically, right, if I have 20 bits, so maximum it can store 40 memory units. But if I have a 20 qubits, right, here it scales exponentially. I can keep 2 to the power of 20 qubits in 22 to the power of 20 memory units at one go, right, which is nothing but a million values in parallel. And then if I have a 50 qubits, I can build a computing power which is equivalent to China's supercomputer, which is Sunway Taihu, right? That's a powerful supercomputer available in the world today, which is approximately 100 petaflops of data per second, right? It processes that much. So, and then if I have a 300 qubits, that's larger than the number of atoms in the observable universe. So how could I do that? Two concepts here. You don't worry if you don't get it. You need to first build a qubit. How do you build a qubit? Put the subatomic particle into a spinning position using, there are various ways to do it. I'll explain that in the later. And then take two or multiple qubits and then entangle them together. So once you entangle them, you can untap this power of the qubits. And then with just a handful of qubits, right, with 50 qubits, you can actually build a supercomputer with this theoretical. And then also this also comes to a concept called quantum supremacy. What is quantum supremacy? If I could able to do a task using a quantum computer, which cannot be replicated using the a physical computer, right? Or I could able to do faster than a physical computer, that's called quantum supremacy. I can give you a classic example, right? Google, using its quantum computer called Sycamore, generated a random number beyond, I think, 40 digits or 50 digits. A physical computer simply could not able to do it, right? It doesn't even, they try to find it, if there is a physical computer who could able to generate some random number beyond 40 digits, there is no physical computer which could able even generate a random number beyond 15 to 20 digits, because there is a limitations with your computing power. So this is exactly what the quantum supremacy is. So you could able to achieve something using a quantum computer, which is not possible using a physical computer. That's called quantum supremacy. And then China, what they did, a quantum computer made by researchers in China solved a calculation in 4.2 hours, correct? That would take classical computer 1,005 years. This time, of course, this is what is called as quantum computational advantage or quantum supremacy. You know how many qubits they used? Can you guess how many qubits just they used to achieve this supremacy? Just 6 qubits. And then they broke the record of Google, obviously, right? So that's the power of quantum computer. So it's very powerful computation that you can build with a handful of qubits by tapping the quantum concepts, entanglement and qubits, and that's where you achieve the quantum supremacy. How do you build a quantum computer? So this is all good. So, but then, do you know how do you build and use the quantum computer, which is what I briefly explain in my next topic, right? So this is just a graphical explanation of what is regions of quantum advantage and quantum supremacy, and I think it's a self-read. As I said, anything beyond this particular zone is where you use quantum computers, right? Which simply cannot be done using the classical computers. And there are some use cases where you have quantum advantage. Maybe you can do with the physical computers as well, but you can perform even maybe slightly faster than that. So just a theoretical concept. Maybe you can take it and then read it, self-read it. But if you look at the quantum computer architecture, right, it's very simple. So what's happening here is you still need a classical computer, and then you still need your classical software and data to access the quantum computer. The quantum processing power is what we need to put it in the backend. So in a way, if you go to the IEEE, right, what happens is there is a quantum register and then the physical and logical circuits, and then there are quantum gates and measurements that are built, which is electronically wired, and then as an interface, right, as like an output gateway, it'll give you to the classical computer. So meaning whatever the calculations that happens inside the quantum computer, it'll still needs to pass through a classical computer, and that's where you use another software and data available to interact with this. So it means that if someone says that, hey, for a quantum computer, I need a different type of a machine to access it. No, it's still your classical computer connected in the backend to the quantum computer. And also, this is again a slightly scientific topic, right? There are various companies exploring various ways to build that build the qubits that I explained here. Correct. So here I told you, right? I think you spin the subatomic particle. So basically, what's happening? It's called superposition. You put them into a spinning position. I think the different companies uses different ways to build these qubits. For example, classical way which Google, IBM does is, they cool the atoms to a superconducting temperatures close to Kelvin degrees, minus 273 degrees, and then put them into a superconducting loops, right? And then tap that power to put them into a superposition. And then also they use, some of the other companies uses lasers and then activate the atom to put into a superposition. And then that's called trapped ions, silicon dots. And then also there are companies which uses the vacancies between the diamond structures, right? And then naturally use them to build the qubits. It's very scientific, at least for students, you can explore what this is, because each and every method which I've shown here, right, it's been adopted by major companies in the market. So some of the companies like D-Wave, companies like IonQ and all, they're using the trapped ions. Google, IBM, Honeywell, they're using the superconducting loops. Intel is using this particular method. Microsoft is using the topological qubits and so on and so forth, right? So various companies are adopting various ways to put the quantum computer into use. I think that's the technical portion of it. I want to cover all these concepts, but at least even if you don't get it, you should at least get familiarized with what is a qubit, what is called superposition, and then what is entanglement, and then how do you tap the entanglement to achieve the quantum supremacy. And then basically all these how it works to build a quantum computer. Correct? So if you don't get it, take these 2 slides and then do the research. I think from now on, right, it's all going to be a layman and business understanding of quantum computing. Okay, so you heard about how to build a quantum computer, right? Where is it used? I told you, right, with just 6 bits of qubits, Chinese scientists were able to calculate something that takes 1,005 years into 4.5 hours. Correct. So which means that the first and foremost application is to tap that calculation power. You can do a lot of wonders in the current market, which cannot be done by your so-called computers, your physical computers. So basically, a lot of enterprises wanted to have a physical quantum computer with them so that they could able to do a lot of calculations. I'll tell you which industries will use later, right? And also, there is another interesting concept called quantum communication. I don't know if you go through the news very recently, right? Last few months back, there's been a news on ISRO, Indian Space Research Organization. They've done a quantum key distribution across 300 meters and beyond, right? And then also, if you see last year, China could able to build a quantum encryption method into the space. So that means it launched a satellite into the space, and then it communicated with that satellite, which is like thousands of kilometers away, using a quantum technology. It's called quantum communication. So basically, what's happening here is when you entangle 2 qubits, right? For example, I have a qubit 1 and qubit 2, and then without breaking the state, if I separate it, this particular qubit, I put it in a box, and then without disturbing the state, I can put this box, say, for example, in Singapore, and then take the other box, maybe, for example, to Hong Kong or even India. it is still entangled as long as the state is not disturbed. Meaning if I change the state here, the second qubit's state also changes, and nobody knows how it happens, right? Einstein calls it spooky action at a distance. I think you can also research on this. That's the mind-blowing characteristics of quantum principle. And then imagine this can be used for quantum communication. For example, this is exactly what happened, right? So India, the ISRO scientists in Ahmedabad, they separated, they put two qubits into entanglement, separated by 300 distance, and then by changing the quantum states, right, they could able to communicate a message to the other scientist who are 300 meters away, and then that scientist can crack it. And there is no connection in between. For example, if you take the current communication, right, there are satellites and there are lasers, satellites, and then you have your cable links, right? Hackers can tap that and then encrypt that information if they have that power. But in this case, right, there's no connection at all. So that's where the quantum communication is proven very powerful. And then the other important application of quantum computers is quantum sensing. So what happens is if you analyze the sensors data, right, that are available today, if you do it using the physical sensors versus the quantum sensors, right, at least in terms of the accuracy, you'd be able to capture nanoseconds or even beyond the level of changes that are happening in the sensor data. So the physical sensors could able to get between, say, for example, a millisecond interval. You can bring that down to a nanosecond and even accurate measurement of the data. So which itself is quite critical when you're measuring the earthquakes or measuring the lattice structures in the chemical compounds and so on and so forth. So these are the three key applications. You keep hearing these terms again and again. If you go to, I don't know if you're following me in my LinkedIn, I share most of the topics related to these three. And then across the globe, any quantum application that you see fits into any of these three. Correct? I can tell you what and where this particular items are used, right? For example, this I've taken from Deloitte. Both the slides I've taken from the Deloitte, right? As you could see, healthcare and life sciences, theoretically, it's been proven that you can find the drugs faster. And I was talking to the UK Quantum Center for Technologies, right? The UK quantum computing folks. In fact, they used quantum computing and then they accelerated the genome mapping by 25 times using the quantum simulators, not even the quantum technology. It's quantum simulators is what they used. And similarly, financial services, there are lots and lots of use cases. I also mentioned this during the fireside chat with Piyush. For example, most of the investment banks, because that's where the money is, they could able to collaborate with these quantum computing cloud service providers and then hardwares. And they're implementing the quantum services into financial services. For example, a classic example is credit origination and onboarding, right? A loan, if I give you how credit worthy you are. And then the current modeling will require a lot of computing power, and then it does not take a lot of parameters into consideration. But if I model that credit analysis using the quantum computer, I could able to extract the data at real time in a milliseconds compared to the hours and hours of crunching. And then similarly, for a big bank like Bank of America or OCBC or DBS, right? If I need to calculate their financial risk, it takes about 1 month or 20 days or 15 days to do it because the crunching requires so much of time, right? And then if I use a quantum computer and model everything, I could able to get a real-time risk of the bank and so on and so forth. That's where most of the jobs and then most of the career opportunities are coming in the US and also in Europe, financial services. And then other than that, the natural resources, supply chain, right? And some of the supply chain related aspects is where it is being used. For example, China, especially the company where I come from, Alibaba and Lazada and all these companies, right? So we have thousands and thousands of vehicles. Imagine we have like 60,000, 70,000 fleets only in Indonesia. And across the globe, if you also add Alibaba fleets into the consideration, right, in China and AliExpress fleets, etc., so it runs into the millions. So if I have to come up with the optimized warehousing strategy and the routes to the customers, physical computers simply could not able to solve the problem. I model all these optimizations into a quantum computer. At least we are using something called quantum simulators, and our Alibaba Demo Labs is like trying to solve some of these supply chain logistics optimization problems. So, and also last but not the least, right? People are also combining AI and quantum computing to train the models faster. Correct. So here, Google even released something called TensorFlow Quantum. It is called TFQ. So basically, what happens here is you can train the models faster if you could able to embed the data into a quantum computers. And then it has been classically they're trying to prove that let's say if a normal model takes about 5 hours or 6 hours to run, I could able to train them in seconds using a quantum computer. So all these are theoretical, of course. Okay, so many advantages and then mind-blowing computational powers with the quantum computing. What is the current state, right? What is currently happening? Do you know how a quantum computer even looks like? Does anybody seen a quantum computer? Maybe a few people in the call are familiarized with the concept, but what is this? This is exactly how a current quantum computer looks like. Can you relate to the first slide that I've shown? ENIAC, right? Where there are a lot of bulbs, a lot of transistors in a room where the calculations are all happening. The quantum computers are exactly in this stage, because remember what I said? You need to cool down. You need to first capture a atom, or you need to take a molecule, and then you need to cool it down to close to Kelvin degrees, which is a superconducting material, which cannot be operated at a room temperature. And then to do the superconducting cooling itself, you need lots and lots of electronic circuits, etc., to do that. Correct? Which is exactly what is happening. And then the actual processor is somewhere here. Correct? You can't see that basically in this picture. So here what happens, all these cooling and then the circuiting will happen, and then put that molecules, atoms into a superposition and then entangle them, right? Using the microwaves. And then using that entanglement, there is a computational power that are being used and calculated. And as you could see here, right, even though this is my quantum processor or a quantum computer and integrated circuits, all these are flowing back to my physical computers here. So basically here, the measurements and all are stored and calculated and used in the physical computer. So, and then in this case, it's a cloud-based computer, I would say. So if I have a system, I can create an account in the Google Cloud, especially where you can try the quantum simulators, right? And then that quantum simulators are connected to these machines that you see here. And then you can simulate some of the calculations here. Similarly, I think this is Honeywell's so-called, at least on paper, most advanced quantum computer available in the market. Even you see, right, it's very huge, very big. And then it's not like your phone or a watch or a laptop where you could able to achieve something, right? So this is exactly relates back to how the computers were in 1950s. So which comes to the current state, right? So do you think all that is okay? So meaning I can simply use even maybe some of these computers. What if I put 1,000 qubits and then bloody achieve the scientific advancements that nobody can do? Is it possible even to build 1,000 qubits? May not be, which is what I will explain in my next slide, right? Current state. So are we there at some of the key challenges with a quantum computer, right? It's called decoherence, error correction, and output observance, and obviously the cost. These are the four fundamental factors. So what's happening here is, remember entanglement? I told you need to put 2 qubits which are cooled down using the to cool down to a 0 degree Kelvin, and then use a microwaves to entangle them, right? And then you need to maintain the state to derive the computational power for it. But what's happening is, decoherence is, even if your temperature changes by milli-degrees, not even 1 degree, right? Milli-degrees, the state will break. So that means the scientists are struggling to maintain the particular states between these qubits for a very long time. And then also error correction, right? Because you cannot say that the output of the quantum computers are like zeros and ones, because we are putting into a probabilistic positions here. The measuring is also probabilistic, so which also comes to the output observance, right? There is a lot of noise and error involved in calculating the quantum computing. So that means you can only know the answer at a certain probability. With 80% confidence, I know that, this is my factorial decryption looking like. And on top of that, you've seen these things, right? Very, very costly to even build something like that. So which is why I think currently what's going on, instead of private companies, a lot of quantum computing is being spent by the governments. For example, Japan, US, China, and UK are very, very dominant in this. China especially, right, is very, very, very dominant in this technology. So every day or the other, they're doing some of the other advancements. And then, as you see, right, they have almost 3,000 plus patents on their name with regards to the quantum computer. And as I showed you the example, when Google achieved the quantum supremacy, the China broke it like within like an year. And which also gives me a fundamental state, right, or at least the current state of the quantum computing. Lots and lots of companies are still in the research phase, so they're investing lots and lots of money into the research in here. And then, what do we have now? Currently, do we have a quantum computer? No, we don't have a full-fledged quantum computer to use, right? With 6 qubits, 5 qubits, anything less than 20 qubits, you cannot really call it as a quantum computer. Rather, you can call it a quantum simulator. You can simulate what quantum computers can do, right? So meaning a lot of the use cases will give you a quantum advantage, but not the supremacy. So meaning you can still do it with the physical computers, maybe slightly faster and then slightly some advantage, but still not all the quantum simulators that we have in the cloud is not a full-fledged quantum computer. We have simulators, and also we have something called quantum accelerators. So here, I would say, just like how we have GPUs in the computer, right? If I have a normal computer, I can plug in my NVIDIA graphic card and then increase my computing power. So in Australian-based companies are working to come up with a quantum GPUs. So meaning it cannot 100% give you the quantum computing power, but at least 20%, 10%, 5% power that is needed, and then it can still boost your calculations and so on and so forth. And then most of these services are available in the cloud. So that means you cannot have a quantum laptop or a quantum watch or a quantum phone to operate. So most of these, as I said, they're all available here, and then through which it's connected to the cloud, and then you can only tap these services and simulate them using the cloud. Correct? So what are some of the companies that are very prominent? As I said, the universal gate-based quantum computers, Alibaba was there, and then Rigetti, IBM, Google, Intel, they're all using this, right? And then there is a concept called quantum annealing. As I said, you trap the ions and then use it and all that. So that's IonQ. And then there is a different type of quantum computing where you build the qubits. And then companies like D-Wave, QNN Cloud, belongs to this particular category. And then also there are these are all hardware related, right? But you also have something like companies specifically working on quantum circuits. And then some of the companies like Xanadu and all, right? They're coming into like a quantum AI. So they're researching, or they're at least building products where you can use AI and quantum computing together. And then, as I said, right, you also need a different kind of a software. Our current operating system or current operating software that we use is not sufficient. You need a different type of software to interact with these quantum computers. There are quite a bit of companies that are working on that, and cloud computing hardware, and there are companies focusing only on the encryption and so on and so forth. So, but predominantly, I would say 80 to 85% of the use cases which the financial services or some of the logistic companies or even the chemical companies, right? They tap the power of cloud. I can show you later what that is, right? How does that look like? Or maybe I can see if I can spend some time here and show you how does that look like, right? Yeah. So anybody can actually simulate and use the quantum computing now, right? So for example, you have something called IBM Quantum. It's very easy. You can just have an IBM account register, and then you could able to tap their computing power here. As you could see here, right, you can even simulate some of the quantum computing capabilities with Python, or you can use their cloud-based services, and then you can build your own quantum circuits as they're showing here. You can see here, right? These are all gates and quantum circuits built, and then basically what they're trying to do, whatever the use case that you have, you try to simulate it using the quantum computers. So there is something called Qiskit, using which you learn how to build your own quantum use cases, right? Using an IBM quantum computer. So it's there. So that means what I meant to say here is it's available to public now, and then, as I said, you can try yourself. Maybe after this, probably you can go and then have an account with IBM, try some simple circuits, and then try how the quantum computer looks like. So with that note, right, I think it'll easily take about 5 to 10 years to achieve the quantum supremacy, right? At least to have a workable quantum computer. Until then, these quantum simulators and accelerators are continue to evolve. It's going to explode in next 5 years. But beyond 5 years, I think I'm sure there's going to be like a breakthrough happening in the quantum, and most of the computers that you have at that time will have a quantum supremacy, correct? And then you also need so key milestone also, you're going to see a lot of open source quantum modeling and training frameworks, and then you also have compelling AI apps that are coming into the future. So just on a note of the way I summarize this slide, currently it's in the research phase, and then you still have simulators with which you can solve a lot of live use cases. In fact, companies like banks like BBA and banks like Goldman Sachs, and then even Credit Agricole, they all used quantum computer to solve some of their banking problems, even using the simulators. So imagine if they have a quantum computer, right? They can go over and beyond what they can achieve. So which means that it's a critical technology that you need to keep watch on, especially students. I think this is your opportunity to get into the field, and then right through that growth curve, right, in next 5 years. And surprisingly, all the governments are pumping money, and you will not believe, right? Singapore started investing in the quantum computing, one of the first countries to invest in the quantum computing, even 10 years back. So in 2008, 2009 itself, they know what the quantum computer can do. And then they built a lot of ecosystem to help us, to help the economy to utilize quantum computing. I'll explain probably in the upcoming slides. But Canada is also one of the initial companies which came into the space. But overall, right, there is like $25 billion of money flowing into the market. And then as of now, in terms of the advancement, China and UK are highly advanced economies. In fact, UK simulated a quantum network, right? Remember, as I said, you need to entangle, and then you can speak to entangled qubits anywhere in the world. They built a quantum internet using the quantum qubits. They simulated some of these folks simulated in the Europe, right? Especially the UK folks. And as I said, Australia is working lots and lots of hybrid, so-called your quantum accelerators. So a lot of money riding through this concept. And then with this note, probably I think I'll not spend much time, but the way I would look at this particular slide is how companies are adapting the quantum computing, right? Do you need to, if you ask me, does your company really need to get into the quantum computing? May not be. So assess your company's needs, right? Is that does your company needs to adopt niche and emerging technologies to stay relevant in the market? For example, startups, late stage startups like us, right? Big tech companies, Lazada, Alibaba. What happens? So they rely on technology. So they live on technology. So they need to solve problems using the technology on day-to-day basis, right? For us, yes, we might need to get in. Or even the example that I provided. Investment banks, Goldman Sachs and all these companies, right? They have tons and tons of money. And then can they use this money to invest better? Yes, they would. So companies like them are the initial ones who get into this right of the quantum technology, right? And then build the simulators and then solve some of the problems. And then that actually gives them a quantum computing advantage over the competitors. So which is where I think how they do it, first, they put some solid 3 to 4 use cases. And then very importantly, they collaborate with cloud service providers who offer the quantum computing, take their expertise, talk to their scientists and then their engineers, and then in collaboration, they try to solve these initial use cases that they put. That's why the cross collaboration, not just with the vendors, but also some of the key consultants in the markets are crucial. And you also need to have a very good team internally to drive all this, right? For example, Goldman Sachs are one of the first persons who could able to recruit a chief quantum officer, CQO. His only role is to promote the quantum computing into the company. Otherwise, all the other companies are starting really slow. They need to understand how the business value is, or even they might want to closely educate what's happening in the industry, wait for 5 years, and then take action and adopt iteratively. And then you really need to understand the hype and the reality. If you don't, then this might lead to the disillusionment, right? And then that's why setting the right expectation is the key. It's not your magic wand solving all the problems. So you need to understand what quantum computers or accelerators or simulators can do at the moment. So with that note, I'm venturing into the last and important aspect of this topic. Do we have, at one side you're saying it's a niche technology, a lot of money on the research. Do we have enough career opportunities? Or at least in future, do we have like a good career opportunities, or someone like students can start now to capture that wave, right? So this is what I'm going to focus on. People realized it's going to be very important to have a quantum skill set, right? Which is where I think the New York Times and Forbes and a lot of other newspapers and research organizations very well aware that you need to build the quantum skills starting now. There's going to be a huge talent shortage with this. For example, Australian quantum technology industry could able to generate 4 billion revenue, right? So then 16K new jobs every month. That's almost like how the computer industry worked in 1960s or 70s. So it's going to be a next revolution in which you definitely need to have a good adoption of skills. So I take the classic example of different roles that IBM put it, and then I can explain what are the different career paths that are possible in here, right? Especially if you're students or data scientists or software developers, I think give some time here on the slide, correct? Very important slide. As I said, most of the careers are focused on research-based roles between 2020 to 25. Next 5 years, majority of roles that you have currently is career focused, including Singapore. But if you go to US and Europe, there are niche roles that are emerging, non-technical roles or combining AI with quantum, because as I said, they're also building lots and lots of products and software frameworks that can talk to quantum computers. There is also a development roles that are possible, right? There is, but by then, compared to the research roles, the other non-research roles are, I would say, only 10%, 90 to 10%. But 90% of the roles currently are research. So which is why if you're an electronics and electronic student, engineering student, right? I think a lot of opportunities in US and Europe. In fact, some of the universities are offering courses, technical quantum computing courses, right, to get you onto the speed. I would also recommend you thinking about doing a PhD in quantum computing, especially if you're keen in Singapore. NUS has a very strong foundation in this topic. So they're collaborating with AWS, they're collaborating with universities in Sweden and Switzerland and UK, and talking to the Canadian quantum ecosystem, and then trying to learn what they've done and adopt their own quantum ecosystem in Singapore, right? So NUS is very strong player here. I think you should seriously look into it. But otherwise, lots and lots of technical courses in US and Europe. If you're a non-technical student, right, I would say not so many opportunities as a fresher. That means in next 5 years, there's nothing you would really get. But you continue to do your degree in your course. But if you're keen on getting into the non-technical area of quantum computing, you need to look at some of these courses online. For example, as I've shown you, the Qiskit summer school, right? This comes every year, and then they teach you at a layman term, right, what the quantum computers are. It's like almost like a 4-day course where they make you hero from zero, right, in the quantum computing. And if you're a non-technical guy, you should look at something like this. And then if you really don't have time to attend all these Qiskit summer school programs are also available in the YouTube, right? There is a playlist which you can use, and you could able to understand what they taught you in the Qiskit school. As you can see here, introduction to quantum computing. There are 38 videos that are available. So on your own spare time, you spend and then get familiarized with this knowledge. And then in Singapore, there is a university called, this is SUGT, Singapore University of Technology and Defense. There are online courses as well, 2-day courses, 3-day courses on quantum computing, and then it will help you familiarized with some of the concepts of quantum computing. And then if you're a PR or a citizen, you can even get the subsidies on the course. Correct? I think you should seriously look into it. And then also, if you're in a mid-career, which falls into the non-technical mid-managers, if you want to keen to understand what a quantum computer is. So you also have enhanced training support for SMEs, and then mid-career enhanced subsidiaries, MCEs. So you can tap this, and then you can learn these courses. This is very powerful because I myself kind of look through it, and then it also collaborates with your Qiskit and then IBM quantum computing, and help you familiarize with these topics. Very, very crucial way to learn these concepts. Amazon and D-Wave and companies like this, they also offer online courses. It's worth exploring them. But yeah, so ideally, what I was trying to say, if you're if you are a non-tech, if you're a non-technical background, I'm sorry. If you're in a non-technical background, spend some time on cloud computing courses. So, but otherwise, most of the focus is on research. And then, surprisingly, right, this is also going to increase. That means if you're a data scientist or a software developer, or if you're electrical engineer and things like that, right, there's a lot of opportunities that's going to emerge in the software and hardware portion of it, especially scientific programming, and then building the new programming languages, graph algorithms, and data structures. So these are some of the skill sets or niche areas which are coming up. And also to show you how these roles look like. For example, Google has some of the non-technical roles, right? They call it head of business operations, quantum AI. So what these guys do, as a head of business operations for quantum AI, you will lead business-related operations with quantum AI. So meaning you collaborate with different vendors outside, operations and partners in marketing. And then it will also, responsibilities include manage initiatives and decision-making of quantum business operations. This is pretty similar to the Goldman Sachs Chief Quantum Officer. Ideally, these kind of the roles help you drive the quantum and quantum AI across the organizations. Some of the hardware engineer roles is pure technical in nature, right? As it says, so basically you need to have a skill-specific requirements to get into this role. For example, they say you need to research on quantum processes and write documentation and so on and so on. Electrical engineers, which falls into this category, right? This particular category, software developers, data scientists, and also electrical engineers. So you have good career opportunities in US on this. It's also worth looking at companies like Rigetti. Rigetti is a product-based company. So you have, again, lots and lots of assembly, test engineers, and hardware engineers needed in this area. And surprisingly, I think in the Singapore itself, you have lots and lots of quantum computing openings. For example, CQT, right? Quantum Information Processing Center, it's requesting a lot of research fellows to join them, right? So if you're already a student, instead of going to a corporate world, you can join their research program. And IBM is hiring data scientists to combine quantum computing and AI. And NUS is asking for a research assistants and so on and so forth. And quantum computing specialists. I think you can explore yourself, right? Currently, you have like about 800 plus jobs only in Singapore. on quantum computing, or 80% of them are skill specific and research oriented. So, which also gets to the next topic, right? How is it, how the ecosystem is evolving in Singapore? How does it look like in Singapore? I think the father, I would say, of our, there are two key organizations that are driving the quantum computing in Singapore, especially the name that you should really look at, that you should focus is CQT, the Center for Quantum Technologies. It's basically a research center of excellence supported by National Research Foundation. And then you know what? It's globally famous. If I put some of the UK related companies or Canadian related companies, right? So it comes into the same category. The kind of research that it is working on, and then the kind of startups that it generated, right? It's one of the world-class organization. And then in fact, the kind of startups that it is generated is these 5 companies, right? Autonomics, as I said, it's working on quantum sensors. And then S15 Instruments, predominantly focusing on quantum key distribution and quantum encryption, right? Spectral, it's a Singapore-based company which works on quantum communication, especially satellite-based quantum communication. There is if you research for a news 2 years, 3 years ago, in fact, Singapore also proved quantum entanglement. That means communicating with a quantum qubit, which is in satellites, right? And then use these satellites to distribute the keys across different parts of Singapore. So Spectral is in the center of that. And then on the other hand, there is also computing companies like Horizon, which focus only on programming side of it. They're building the quantum computing softwares to interact with quantum computers. Similarly, Entropica Labs is just like IBM or Honeywell or Google. They're building their own cloud-based computer offerings, and very, I would say, strong player in Singapore. These 5 companies, and then there are small bunch of startups, right, are fundamental foundation for Singapore's quantum ecosystem. And it's one string, right? Meaning here, the idea here is CQT will do lots and lots of research and spin off through multiple startups. But there is another organization called Quantum Engineering Program, QEP. This is again funded. It's a Singapore to build its national quantum safe. So basically, this is Singapore government entity, right? Which predominantly focuses on solving some of the user-defined problems, which research grants, and they also built a different kind of students and research-based ecosystem. In here, it builds a company form-based ecosystem. Here, it fundamentally focuses on the research, and it has been supported since 2018 by National Research Foundation. Both are supported by National Research Foundation, correct? And then this particular organization also collaborates with NUS, AWS, IBM to boost quantum skills in Singapore. So the course SUTD that you saw, it's I think it's one way. It's part of the same collaboration that we're talking about here. And then also it has got another a spin-off called KAIRA, the Quantum Young Research Association. It's a community of young quantum researchers in Singapore, right? So from postdocs to undergraduates who are doing their final year projects, who has got new association of working in their interest, right? They can be part of this Quantum Young Research Association, and then they tend to organize the academic events and also give them use cases to solve, speak into the industries, and then plan social gatherings, and then basically motivate these young researchers to accelerate in their quantum topics. Correct. So very strong ecosystem. I would say a lot of other companies, even for example like India. Or some other companies, right, or some other ASEAN countries, they're still not there yet, correct? Comparative to Singapore, UK, and Canadian, Chinese markets, they're not there yet. So again, as you could see here, they focus on 4 important parameters: quantum communication security, quantum computing, quantum sensors, and then National Quantum Fabless Foundry. This is important. They're also wanted to build their own fabless foundry, right? They want to develop their own hardware in terms of the technology. and then which is very critical for Singapore as a nation to move ahead. With that note, right, I think a few key takeaways quickly before I get into the Q&A. Quantum computers are inherently different to classical computers. We need computers to interact at subatomic level and perform calculation faster, and you need nature to model the nature, right? So that's where the quantum computer will come into the play. Quantum computers works based on quantum mechanics. The power of quantum computing is derived based on entangled qubits. Right? As I said, if you have 300 qubits, that's the observable number of atoms in the universe. So you're able to get so much of a computing power that'll be equal into the observable number of atoms in the universe. And then you can unlock more business value by combining quantum and AI. And then predominantly it's used in three fundamental areas, right? Quantum computing, quantum sensors, and quantum communication. So these three in various industries are continue to drive lots of changes. And then also key takeaway from today's session, there is a hype and there is a reality. Even though in one way, theoretically, quantum computer can do most of the wonders. Currently, all we have is simulators and maybe a hybrid accelerators. We don't have a workable quantum computer yet. So we're still at 50 qubits, 40 qubits, 30 qubits, 6 qubits, not connected, a lot of noise, and then it's not stable and so on and so forth, right? So which means that we still don't have a workable quantum computer. We have simulators. Even using the simulators, which are cloud-based, can derive lots and lots of use cases, correct? And leaders who wants to have a competitive advantage can get into the quantum computing, but otherwise, slow iterative investments are what is required. Last but not the least, in the careers beyond Singapore, a lot of opportunities in Singapore, but otherwise predominantly 90% of the jobs focusing on the research or skill-specific roles, right? Only 10% are non-technical roles, which also says that the industry is evolving on research, building those workable quantum computers before it could able to explode to the non-technical roles. And I think Telugu Samajam will also share this particular slide later. This is your ready reckoner, right? So maybe if you want to research on some of the topics later, you can use this and ready reckoner. If somebody asks you what is a qubit, you can quickly refer and then answer them. It also talks about supremacy, entanglement, what is a quantum computer, how many qubits in today's system, different ways to achieve the qubits, difference between a quantum and classical computer. Right? This is very important slide. Keep it as a ready reference, and then you can go deeper into each of these concepts and then do the research yourself. Just like how I put last time, you can read through this disclaimer. These are my thoughts, right? Not my company's thoughts or some other thoughts. And the material used in this are copyrighted. Please don't reuse it or replicate it without Telugu Samajam or my permission. And it is also essential to know that some of the recommendations that I provided is based on my experience and my own understanding. If you want to apply for your own company, or if you want to apply for your own use cases, you need to be carefully thinking, do your own research, and then apply all that, correct? And then I do not endorse any of the cloud-based solutions that I shown here, right? IBM's, Google's, or D-Waves. These are some of the examples that I showed. I don't basically promote any of them. So with that note, I think thank you so much, Telugu Samajam, for giving this opportunity, right, to connect with local community using ST Connects and able to teach them new today. Every day, we learn something which is already there, but sometimes we learn something new. I think today is that day, right? Some of the people who doesn't know quantum computer, at least they're going to walk away with some basic knowledge of what that is and then importance of particular technology, right? With that note, I think I can move on to the question and answer session. Anil, up to you.
Yeah.
Over to you, right?
Yeah. I have a few questions, Muni.
Yeah, go ahead.
First question, what are some beginner-friendly quantum online platforms for free? I think you mentioned IBM, but people want to know if there are any other.
Yes. So D-Wave, go for D-Wave as I shown. IBM Qiskit is one. And forget about using the quantum computer, right? If you want to familiarize with the concept as well, Massachusetts Institute of Technologies offers a course called XPro. So it will take you through a deeper understanding of what the quantum computers are, and it'll give you the non-technical way, right? I think you should adopt that. But otherwise, D-Wave, IBM Qiskit, AWS Bracket, if you go into these portals, So you can yourself learn and even simulate some of the use cases. At least I remember I've done, using the Shor's algorithm, right? I could able to replicate that Shor's algorithm to break the encryption using the IBM Qiskit in one of their first interactions. You can put drag and drop, you can build the circuits and then solve that. If you want to experience that, you can do that. And I'm using some of the Python based scripts to interact with these IBM quantum computers. You learn all that in the Qiskit. But still, let me remind you, these are very basic simulators, not quantum computing use cases.
Thanks. So there is another question. Actually, in the basics, you mentioned about qubits, right? So the question is about qubits used for both processing and construction of memory.
Ideally, yes, in a way, right? If the state is maintained, even the memory and the processing power is maintained, both.
Okay, hope Shalini, you have answer for this your question. So next question: what are the current day use cases?
Current day use cases, as I said, right? I gave my Alibaba Lazada example. If I have 60,000, 70,000 fleets per country, and if I have millions of fleets altogether, right? If I have to design a optimum, fleet strategy, routes, which routes, what fleet should go, right? A physical computer cannot solve. You need a quantum computer to deal with it. So, and also another financial services example, maybe, right? BBA could able to train a credit model. So meaning how credit worthy the consumer is, right? A banking consumer is through a quantum simulator, much faster and much accurate than a physical computer. They released a paper also in the today's world, right? I think you can take a look at it. And I think also, as I said, the UK-based gene mapping company could able to accelerate their gene mapping 25 times using a IBM quantum accelerator or a quantum simulator. These are classical 2 to 3 use cases. At least that gene mapping, I spoke to the people myself, and I was indirectly involved in the conversations with them. Right, outstanding results. I think it takes about 3.5 years to map a gene in China and Asia origins. They could able to achieve this within 1.5 months using a simulator.
Any info as of now regarding quantum happening in cyber security arena?
Yes. As you could see, I think one of the quantum companies that I talked about, which one is that? In Singapore, called S15 Instruments, right? It's working with Singapore Defense, coming up with quantum key distribution, and then use a quantum-based encryption, right? And then it's going to revolutionize the Singapore government's cyber strategy. And then not just that, that's a government-based entity, right? Supporting the government-based companies across the globe. There are many companies that are researching on cybersecurity, encryption, and decryption using the quantum computers. For example, MagicQ, TACQBit, QNU, IDQ. I think if you see the slide in slide number 19, if you get the slides, it's there. You need to look at the section called quantum encryption. In that section, I think clearly mentioned.
Next question: any engineering 4-year degree courses available in Singapore universities?
NUS has a PhD available in this, not a 4-year degree universities, because the way it happens is you do your electronics and electrical engineering, right? And then after that, you go take this NUS PhD program, which is like 2-year, 3-year program, which will get familiarized in this topic. But the other way to look at it is, if you're a technical engineer, you do this. Some of the European-based Spanish and Swiss, Spanish and UK-based universities, right? They offer a master's, a 1-year, 2-year master's in quantum computing. Maybe I can see if I can share the links later. That's I think a recommended path.
Are there any forums you can refer us to network with people studying or beginning on quantum computing?
Yes, SG Innovate. Register yourself in the SG Innovate in Singapore. They're driving lots and lots of quantum use cases. And then there are also previous videos which you can see and tap, right? They are very well connected with all the ecosystem that I talked about, CQT and all. They conduct series of sessions. And then you can also speak to some of these CQT people, network with them during these interactions. SG Innovate is a good place to start.
So I think I have only those questions so far. Yeah, I think we are reaching to the end of this session. So on behalf of Singapore Telugu Samajam, thank you very much, Mr. Mudi Vinay, for covering a lot of insights and jargons about quantum computing. I know it is a massive topic, but you put up everything in a nice manner to give us the overview. Most importantly, you covered what's happening in Singapore and also in the world. So, and its potential for upcoming years, and where definitely it is useful for the people who are interested to pursue their career in quantum computing.
Absolutely.
So, yeah, I would like to thank you for all your kind efforts in taking up the session today. So, for
Pleasure is mine, Anil. Pleasure
yeah,
is mine.
yeah.
Thank you. Thanks for the
So
opportunity.
I know every one of us truly understood. For the participants, I know every one of us truly understood how important it is for all of us to upgrade our technical skills and integrate with versatile communities to create a positive impact on the society. So we usually hear a lot of technologies, but most of the time we don't know what it is, how to start, where to start, and its prospects. To bridge that gap, STS, in collaboration with other organizations, came up with this free community series. We launched this series called STS Connects in presence of Mr. Piyush Gupta, and also conducted fireside chat with Mr. Piyush as a very first session in November 2021. We are getting experts to take these sessions in this series who have hands-on and real-time experience, not just a training. So we are not going to conduct a training, but we want to give you an overview and just introduce that, respective technology to you, and also its career prospects. And next, after follow-up, what we are going to do is we are sharing these decks and also creating WhatsApp groups to give a little bit introduction and how to, engage with the fellow interested participants. And also maybe experts like Vinay, etc., will be helping you if you have any queries on anything on these particular technologies. We created for data science for last week, and we are going to create for this also soon, maybe next week, 1 week time, not more than that this time. So in this context, we want to reinforce the power of being working together without any cultural boundaries, and can bring us incredible opportunities to network with all intellectual minds, which can enhance our horizons in multiple ways. So to contemplate our efforts, so our request to all of you to share this particular STS Connects initiatives with your family and friends and your circles, so that we will have maximum participation for others, and also they will get benefit out of this. And it gives motivation to organizers and also to the speakers. When we see people are getting benefited, that encourages and gives more encouragement and motivation to us to conduct more series on this. And also we request you to subscribe to our YouTube channel, so where we are recording all these sessions and are available to you all, even if you have missed any previous sessions, or just in case if you miss any later session. So our main agenda for this STS Connects is to create awareness about the changing technologies, thereby empowering communities to update and upskill themselves. We are not limiting this technology, but we have plans related to other topics like education, women empowerment, entrepreneurship, to cater the needs of people from all walks of life in the community, Singapore community. So I take this occurrence to thank STS Management President Kotireddy Garu and other committee members, and also all committee members of other supported collaborated organizations in Singapore. Further, I would like to take my heartful thanks to all the participants, because of whom we are here and able to conduct their session successfully. So last but not the least, we will come up with another interesting topic in few days. So basically for the March month, we will be publishing the details of the session, etc., in due course. So please do tune to our STS Facebook and also our social media, so that you will be knowing what is our next session about. So as I mentioned earlier, so participation is the key. So please do join this and share with your fellow friends and also your circles. So with this, yeah, thank you very much. So see you soon.
Thanks, Anil.